Hello student, in today's lecture we will study about electrochemistry. Chemical reactions can be used to produce electrical energy. Conversely, energy can be used to carry out chemical reactions that do not proceed spontaneously. Electrochemistry is the study of production of electricity from energy released during spontaneous chemical reactions and the use of electrical energy to bring about non-spontaneous chemical transformations. The subject is of importance both for theoretical and practical considerations. A large number of metals, sodium hydroxide, chlorine, fluorine, and many other chemicals are produced by electrochemical methods. Batteries and fuel cells convert chemical energy into electrical energy and are used on large scale in various instruments and devices. The reactions carried out electrochemically can be energy efficient and less polluting. Therefore, study of electrochemistry is important for creating new technologies that are eco-friendly. The transmission of sensory signals through the cells to brain and vice versa and communication between these cells are known to have electrochemical origin. Electrochemistry is therefore a very vast and interdisciplinary subject. In this unit, we will study electrochemical cells and galvanic cells in the first lecture. Please listen to my lecture attentively and note down all the important points carefully. I welcome you once again. Electrochemical cells. Electrochemistry, as you know, is the study of production of electricity from energy released during spontaneous chemical reactions and the use of electrical energy to bring about non-spontaneous chemical transformations. The device which converts chemical energy liberated during chemical reaction to the electrical energy is called the electrochemical cell. Please note, the electrochemical cell converts chemical energy to electrical energy. These cells are called galvanic cells or voltaic cells or Daniell cell. We had studied the construction and functioning of Daniell cell in our previous class. This cell converts chemical energy liberated during redox reaction. Redox reaction, that is reduction and oxidation reaction. Thus, the cell which converts chemical energy liberated during redox reaction to electrical energy is called Daniell cell. It has electrical potential which is equal to 1.1 volts when concentration of Zn2 plus and Cu2 plus ions is unity, that is 1 mole per decimeter. Please see the figure on the screen, on your screen. The figure shows the Daniell cell having electrodes of zinc and copper dipping in the solution of their respective salts. Please see here on the left side we have a solution containing salt of zinc in which a zinc rod is dipped. On the right hand side also we have another container having solution containing salt of copper. This is in which copper rod is dipped and both are connected through a wire. There is also a salt bridge which is dipped in both the liquid as shown in the figure. So, the chemical reaction of the electrochemical cell can be written as Zn, zinc, that is in solid state, plus Cu2 plus in aqueous form combined. Zn combines with Cu2 plus to form Zn2 plus aqueous and Cu in solid form. Let it be equation 1. Electrolytic cells. An electrolytic cell is a device for using electrical energy to carry non-spontaneous chemical reaction. Suppose an external and opposite potential is applied in the galvanic cell and it is increased slowly. We find that the reaction continues to take place till opposite voltages are reached, whose value is 1.1 volt, when the reaction stops altogether and no current flows through the cell. Any further increase in external potential again starts the reaction, but in opposite direction. Please see the figure. The figure shows the electrolytic cell. The left side of the container has an electrolyte in which a zinc rod is dipped. On the right hand side also we have an electrolyte in which a copper rod is dipped. So both these are connected to an external battery or potential as shown in the figure. So if an external and opposite potential is applied in the galvanic cell and it is increased slowly, we find that the reaction continues to take place till opposing voltage reaches 1.1 volt. When the potential reaches 1.1 volts, the reaction stops altogether and no current flows through the cell. Any further increase in external potential, that is more than 1.1 volts, again starts the reaction but in the opposite direction. Now let us tabulate the difference between electrochemical cell and electrolytic cell. Serial number 1. An electrochemical cell, which is also called galvanic or a voltaic cell, converts chemical energy to electrical energy, whereas the electrolytic cell converts electrical energy into chemical energy. In case of electrochemical cell, the spontaneous redox reaction is delta G is negative. We have studied about the change in Gibbs free energy in our previous class. So in case of electrochemical cell, delta G equals negative is negative. Whereas in electrolytic cell, the redox reaction is non-spontaneous. Please underline non-spontaneous, non-spontaneous and takes place only when electrical energy is supplied, that is delta G equals positive. This circuit diagram we had shown in the previous slide. In the case of electrochemical cells, true electrodes are kept in two separate beakers, whereas in electrolytic cell, both the electrodes are suspended in the solution or molten electrolyte in the same beaker. The fourth difference between these two cells is the electrolytes can be different in the case of electrochemical cell. Whereas in electrolytic cell, only one electrolyte is taken. The next difference is the electrodes are of different materials in electrochemical cell. Whereas in electrolytic cell, the electrodes may be of the same or different materials. So there is an option. It can also be of the same material. Next difference is the electrode on which the oxidation takes place is anode. So in anode, oxidation takes place. And the electrode on which reduction takes place is called cathode. That is, left side is anode where oxidation takes place. Right hand side container is cathode where reduction takes place. So anode is negative pole and cathode is positive pole. In electrolytic cell, the electrode which is connected to negative terminal of the battery is called cathode, and the cations migrate to it, which gains electrons, and hence a reduction takes place. The electrode is called anode. Seventh difference. To set up this cell, a salt bridge or porous pot is required. You must have seen in slide number 1 that in the case of electrochemical cell, a salt bridge was needed to connect between the two dipped into electrolytes of the two cells, left cell and right cell. In the case of electrolytic cell, no salt bridge is used. Galvanic cell. A galvanic cell is an electrochemical cell that converts chemical energy of a spontaneous redox reaction into electrical energy. In this device, the Gibbs energy of spontaneous redox reaction is converted into electrical work, which may be used for running a motor or other electrical gadgets like heater, fan, or geyser. So, galvanic cell converts chemical energy to electrical energy, and there is a redox reaction, spontaneous redox reaction. An electrochemical cell consists of two compartments known as half cells. So please recall the figure shown in the first slide, and there you may see that there are two half cells. A half cell consists of a metallic rod, that is electrode, dipped into the solution of its salt called electrolyte. This is the electrolyte. The two half cells are connected by a metallic wire through a voltmeter. This is the metallic wire, and here, though a voltmeter is not shown, we can connect an voltmeter or an ammeter to detect the flow of current. The electrolytes of the two half cells are connected through and internally through a salt bridge. This is a salt bridge wherein it is nothing but an inverted U tube, and which is dipped in both the electrolytes of both the half cells. Sometimes both the electrodes dip in the same electrolyte solution, and in such a case we do not require a salt bridge. Daniell cell is one such cell in which the following redox reaction occurs. Zn in solid form plus Cu2 plus in aqueous form combine, that is Zn and Cu2 plus combine to form Zn2 plus in aqueous form plus Cu. This reaction is combination of two half reactions whose addition gives the overall cell reaction. So the half cell reactions are Cu2 absorbs two electrons to form Cu, that is reduction. Reduction is taking place on the right hand compartment on the right side. This is reduction half reaction on the right side. Cu2 plus 2E, that is copper. So electrons from this flow and it combines with two electrons to form Cu. So a reduction reaction is taking place. On the left hand side, we have zinc rod in solid ZnS, which loses electrons and oxidation takes place. Losing of electron results in oxidation. Therefore, Zn splits into Zn2 plus 2E minus, that is oxidation half reaction on the left hand side. Let these two equations be equation number 2 and equation number 3. These reactions occur in two different portions of the Daniell cell. So please remember the reaction on the left cell is different from the reaction on the right half cell. Half cell is different and right hand side half cell is different. Reactions are different. Standard electrode potential. In a galvanic cell, the half cell in which oxidation takes place is called anode, and it has a negative potential with respect to the solution. So we have seen that a Daniell cell or a galvanic cell has two half portions. So in a galvanic cell, the half cell in which, that is left cell, in which oxidation takes place is called anode, and it has a negative potential with respect to the solution. The other half, that is right hand side half of cell, reduction takes place and it is called cathode. It has a positive potential with respect to the solution. Thus, there exists a potential difference between the two electrodes, and as soon as the switch is on, the position of electron flows from negative electrode to the positive electrode. The direction of current flow is opposite to that of electron flow. That is, the electrons flow from left side to right side, and the direction of current is from right side to the left. At each electrolyte interface, there is a tendency of metal ions from the solution to deposit on the metal electrode, trying to make it positively charged. At the same time, metal atoms of the electrode have a tendency to go into the solution and as ions and leave behind the electrons at the electrode, trying to make it negatively charge. At equilibrium, there is a separation of charge, and depending on the tendency of the two opposing reactions, the electrode may be positively or negatively charged with respect to the solution. Thus, a potential difference develops between the electrode and the electrolyte, which is called electrode potential. Please read this paragraph once again. So, electrons flow from anode to cathode. That is negatively charged electrode. Anode is negatively charged with respect to solution. So, electrons go out of the negatively charged electrode and move towards the positively charged cathode. At each electrolyte interface, there is a tendency of metal ions from the solution to deposit on the metal electrode, trying to make it positively charged. At the same time, the metal atoms of the electrode have tendency to go into the solution as ions I leave behind the electrons at the electrode, trying to make it negatively charged. At equilibrium, there is a separation of charges, positive charge and negative charge, depending on the tendency of two opposite reactions. Hence, the electrode may be positively charged or negatively charged with respect to solutions. Thus, a potential difference develops between the electrode and the electrolyte, which is called electrode potential. When the concentration of all species involved in a half cell is unity. So here we are considering the concentration to be unity, that is 1 mole per decimeter. Then electric potential is known as standard electrode potential. So when the concentration is 1 mole and temperature is 298 Kelvin and pressure is 1 atmosphere, then it is a standard electrode potential according to IUPAC convention. The reduction half occurs on the copper electrode. So please note here, which I forgot to mention. So according to IUPAC convention, the standard reduction potentials, note the underline, standard reduction potentials are the standard electrode potential. In problems also, when we say standard electrode potential, it is invariably standard reduction potentials. The reduction half reaction occurs on the copper electrode, while the oxidation half reaction occurs on the zinc electrode. So there are two types of oxidation potential. On the reduction half, there is which occurs on the copper electrode, which is cathode. So that is the reduction half potential. Similarly, oxidation half reaction occurs on the zinc electrode, that is which is anode. These two portions of the cell are also called as half cells or redox couples. The copper electrode may be called reduction half cell and the zinc electrode is called the oxidation half cell. We can construct innumerable number of galvanic cells on the pattern of a Daniell cell by taking combinations of different half cells. Each half cell consists of metallic electrode dipped into an electrolyte. Cell EMF. A galvanic cell is generally represented by putting a vertical line between metal and electrolyte solution and putting a double vertical line between two electrolytes connected by a salt bridge as shown in the inside box. Similarly, anode is on left and cathode is on right. So the representation of a galvanic cell is, for example, copper in solid copper electrode and its electrolyte is separated by a single vertical line. In the container on right side, silver and its aqueous solution are separated or indicated by a single vertical line. There is a double vertical line between the anode container and the cathode container as shown in the figure, and the equation for this representation is Cu combines with silver 2Ag plus to form aqueous copper solution plus 2 silver 2Ag. The trick to remember these conventions are the word lone, where L stands for left hand side, and O stands for oxidation, A stands for anode, and N stands for negative, that is left side. Similarly, on the right side you have right reduction. On the right side it will be reduction, not oxidation. And similarly, the electrode on right side is cathode and it is positively charged. The potential difference between two electrodes of a galvanic cell is called cell potential and is measured in volts. The cell potential is the difference between electrode potential, that is reduction potentials of cathode and anode. Please remember and read once again. The cell potential is the difference of electrode potentials, that is reduction potentials of cathode and anode. So it is not oxidation potential but reduction potential as per the convention. When no current is drawn through the cell, then the potential difference is called electromotive force. Under this convention, the EMF of the cell is positive and is given by potential of the half cell on right hand side minus the potential of the half cell on the left hand side. The equations in the cell is, the equation for cell is Cu combines with aqueous solution of silver to form aqueous solution of copper plus solid silver rod. So the half reactions can also be written in the cell as the cathode on the, that is on the right hand side. The aqueous solution gains 2 electrons to form 2Ag, and in the anode side, copper rod solid electrode splits into aqueous solution of copper plus it gives up 2 electrons. So when it gives up 2 electrons, it is oxidation. When it gains electrons, it is reduction. So here in equation 5, it is gaining electrons, it is receiving electrons, so it is reduction, and it is giving up 2 electrons, so it is a oxidation. The sum of equation 5 and 6 lead to the reaction 4 above in the cell, and that the silver electrode acts as a cathode and copper electrode acts as anode. The cell can be represented as shown in the representation, Cu and Cu2 plus separated by a single line, as well as silver and aqueous solution of silver separated by a vertical line. Both copper and silver containers are indicated by two double lines. So under these conventions, the EMF of cell is positive and is given by the potential of the half cell on the right minus the potential of the half cell on the left hand side. So right is first and right minus left. So E cell is equal to E right minus E right. It can be seen that E right is E cathode and E left is E anode. So therefore this representation E cell is equal to E cathode minus E anode. Measurement of electrode potential. The potential of individual half cell cannot be measured. We can measure only the difference between two half cell potentials that gives the EMF of the cell. If we arbitrarily choose the potential of one electrode, that is half cell, then the potential of the other can be determined. According to the convention, a half cell called standard hydrogen electrode SHE, as shown on the screen, is assigned a zero potential at all temperatures. This cell, the standard hydrogen electrode, contains a platinum electrode coated with a platinum black, as shown in the figure. The electrode is dipped in an acidic solution. This container has an acidic solution H2O plus, and hydrogen gas is bubbled through it. The concentration of both reduced and oxidized forms of hydrogen is maintained at unity. This implies that the pressure of hydrogen gas is 1 bar and the concentration of hydrogen ion in the solution is 1 molar. 1 molar as shown here. This is oxidized form of hydrogen and this is hydrogen gas at 1 atmosphere. The standard hydrogen electrode is used as a reference electrode whose electrode potential is taken as 0.00 volts at 298 Kelvin. This is the room temperature, standard room temperature. In SHE, hydrogen gas is bubbled through 1 molar H plus ions at 1 bar, 1 atmosphere. It consists of platinum electrode coated with platinum black. So the equation for this cell is H plus aqueous plus E minus, that is the aqueous solution of hydrogen gets one electron, combines with one electron to form half H2 gas. That is taken as E naught, is the standard potential, electrode potential equals 0.00 volts. At 298 Kelvin, the EMF of cell, standard hydrogen electrode, and the second half cell constructed by taking standard hydrogen electrode as anode, that is the reference half cell, and the other half cell as cathode, gives the reduction potential of the other half cell. If the concentrations of the oxidized and the reduced forms of species in the right hand half cell are unity, then the cell potential is equal to the standard electrode potential E R naught of the given cell. So it can be written as E naught, standard electrode potential, is equal to E R naught minus EL. So as EL naught for standard hydrogen electrode is 0, then E naught equals ER naught, because ER naught is 0 for standard hydrogen electrode. We can take some examples. Example of the measured EMF of the cell. So take for example platinum solid, hydrogen gas and hydrogen aqueous. That is the standard. This is the left side is anode, and this copper with its electrolyte is taken as cathode. Then E naught of cell is equal to 0.34 volts. That is equal to ER naught is equal to 0.34 volts. So these values are shown in the next slide in the form of a table. The standard electrode potential, therefore, of copper in a copper Cu2 plus aqueous 1 molar solution is positive. This shows that ER naught cell of the cell is positive 0.34. So it is positive and indicates that copper is Cu2 plus is reduced more easily than H plus ion. That is, hydrogen can reduce copper ions. So the reduction is Cu2 plus 2E gives Cu. So another example is platinum H2, that is a standard hydrogen electrode with zinc and its electrolyte. So zinc cell, the E E E naught cell is minus 0.76. These values taken from the table shown in the next slide. Therefore, ER naught is equal to minus 0.76 volts. These are the measured values. The standard electrode potential of Zn2 plus with copper is negative, which indicates Zn can be reduced hydrogen ion. The standard electrode potentials are very important, and we can extract a lot of useful information from them. The values of standard electrode potential for some selected half cell reduction reactions are given in the table on your screen. If the standard electrode potential of an electrode is greater than 0, then its reduced form is more stable as compared to the hydrogen gas. Similarly, if the standard electrode potential is negative, then the hydrogen gas is more stable than the reduced form of species. It can be seen that the standard electrode potential for fluorine is highest. So the electrode potential is highest for fluorine gas, and its a tendency to get reduced to fluoride ions, and therefore the fluorine gas is the strongest oxidizing agent and fluoride ion is the weakest reducing agent, as shown in the first line of the table. Similarly, lithium has the lowest electrode potential, indicating that the lithium ion is the weakest oxidizing agent, while lithium metal is the most powerful reducing agent in aqueous solution. See, this value is minus 3.05. It may be seen that as we go from top to bottom in table, the standard electrode potential decreases with this, and decreases the oxidizing power of species on the left and increases the reducing power of the species on the right hand side of the reaction. Electrochemicals cells are extensively used for determining the pH solutions, solubility product, equilibrium constant and other thermodynamic properties and for potentiometric titrations. Here in this table, ions are present as aqueous species and H2O as liquid. Gases and solids are represented by letters G and S. A negative E naught means the redox couple is stronger reducing agent than the H plus oblique H2 couple. A positive E naught means that redox couple is weaker reducing agent than H plus H2 couple. Applications of electrochemical series. In the previous table, we had seen the standard electrode potentials of different selected materials. So let us quickly revise the applications of electrochemical series. The metal which has low standard reduction potential SRP is more electropositive. The metals which have low SRP value are highly reactive. Alkali metals and alkaline earth metal have low SRP value, so they are highly reactive and evolve hydrogen from cold water. Moderately electropositive metals are less reactive and evolve hydrogen from steam. Weak electropositive metals are not able to evolve hydrogen from water. I will read this once again. Weak electropositive metal are not able to evolve hydrogen from water. The metal which has low SRP, that is more negative values, can replace other metal from its salt. Metals which have low SRP, that is standard reduction potential value, are strong reducing agents. Non-metals which have higher SRP, that is more positive value, are strong oxidizing agents. Metals which have low SRP value, their oxides are thermally stable. Metal which have high SRP value, their oxides are thermally unstable. Now we will answer multiple choice questions. In a Daniell cell, four options are given. The chemical energy is converted into electrical energy. Option B, electric energy is converted to chemical energy. Option C, the energy of cell is utilized in conduction of redox reaction. And option D is potential energy is converted to electrical energy. Please pause the video and read all the four options and mark your answer. You have to remember that in a Daniell cell, chemical energy is converted into electric energy. So mark it. Next question. Which of the following is correct about the given cell? The given cell is shown on your screen. Please examine and analyze the given figure and mark the correct options. Four options are given. Read all the four options and examine your answer, and remember that the cell and the copper is acting as cathode. That right hand side is cathode, left is zinc, that is anode. So this option is given in option C. Please mark it. Next question. The following reaction is taking place in a galvanic cell. Zn forms Zn2 plus 2 electrons, and Ag combines with two electrons to form Ag solution electrolyte combines with electrons to form silver. Which representation is the correct method? So reaction is given and you have to identify the correct representation. The correct representation you have to see here. Zn and its electrolyte is Zn2 plus. Similarly, silver and its electrolyte is Ag plus. This representation is shown in option A. So Zn with Zn2 Ag plus and Ags becomes Ags solid. So mark the option A as the correct answer. Question number 4. Which of the following is correct cell representation? 4 options are given. Zn metal zinc with its electrolyte Zn2 plus and H plus and H2. Option B is Zn with its electrolyte Zn2 plus and on the right cell it is H plus aqueous H2O plus H2 with platinum. And option C Zn ZnSO4 H2SO4 plus Zn. And option D Zn H2SO4 ZnSO4 H2. You have to mark the correct answer. Here in this reaction Zn Zn2 Zn metal Zn electrolyte is Zn2 plus and on the right hand side H2 comma H2 platinum, that is standard hydrogen electron on the right hand side. This option is given as option B. Please mark it. Next question. Next question. The cell reaction of the galvanic cell Cu with its electrolyte Cu2 plus in the left cell and H mercury solution with mercury liquid is 4 options are given. Hg plus Cu2 plus gives Hg2 plus Cu. Option B, Hg plus Cu gives Cu plus mercury. Option C is Cu plus mercury gives Cu Hg. And option D is Cu plus Hg2 plus gives Cu2 plus Hg. So you have to identify the correct answer and remember that Cu is the metal and Hg2 plus is the electrolyte solution. Gives dissolves in solution to give Cu2 plus Hg. This is the correct answer. Which of the following reaction is possible at anode? Please read the 4 options given and identify the correct reaction is possible at anode. Option A 2Cr2 plus 7H2O gives Cr2O7 minus plus 14H plus. So option B is F2 forms 2F minus. Option C is half O2 plus 2H plus gives H2O. And option D is none of these. You have to apply your knowledge and mark the correct answer as A. Question number 7. In cell, zinc with its electrolyte in the left cell and electrolyte copper becomes copper metal. The negative terminal you have to identify. Four options are given. The negative terminal is option A, copper, option B, Cu2 plus, option C, Zn, and option D, Zn2 plus. You have to identify the correct answer and negative terminal you have to see. In electrochemical cell, anode Zn is negative terminal. Here on the left side is anode zinc and zinc is negative. Here also you remember lone, that is left oxidation, anode negative. So option C is the correct answer. Question number 8. For galvanic cell, metal copper with electrolyte Cu2 plus on left side, Ag plus Ag on the right half cell with salt bridge. Which one of the following is not correct? Please underline not correct. Copper acts as anode and Ag acts as cathode. This is correct. Ag electrode loses mass and copper gains mass. This you have to examine. Reaction at anode is Cu for combines with 2 electrons, that is Cu2 plus 2e. Option D is copper more reactive than silver. You have to please read the question as well as the options and mark the correct answer. Copper electrode loses mass and silver electrode gains mass is wrong. Hence, the incorrect option is B, that is Ag electrode loses mass and copper gains mass. Next question. Which of the following is correct under which and in which metals displace each other from the salt solution of their salts? So read the question once again. Which of the following is correct order in which metals displace each other from the salt solution of their salt? So the order is option A, Zn, Al, Mg, Fe, Cu. Option B is Cu, Fe, Mg, Al, Zn. And option C is Mg, Al, Zn, Fe and Cu. And option D is Al, Mg, Fe, Cu and Zn. Please pause the video and read the options again. Given options again. So in a reactive series, Mg is greater than Al, greater than Zn, greater than Fe and Cu. Reactivity decreases. Hence, Mg can displace aluminium, which can displace zinc, and so on and so on. So, Mg has to come first. So, option C is the correct option. Please mark it. Next question. Zn gives hydrogen with H2SO4 and HCl. So, Zn gives hydrogen with H2SO4 and HCl, but not with HNO3, because four options are given. Zinc acts as oxidizing agent when reacts with HNO3. Option B is HNO3 is weaker acid than H2SO4 and HCl. Option C is zinc is above the hydrogen in electrochemical series. Option D is NO3 is reduced in preference to H plus ion. Please pause the video and give the correct answer. Due to reduction of NO3 in presence of H plus ion, H plus ion is not reduced to give H2 gas. Hence, option D is the correct answer. Please mark it. Next question. Fluorine is the best oxidizing agent because it has A. Highest electron affinity. Option B. Highest reduction potential. Option C. Highest oxidation potential. And option D is lowest electron affinity. Please pause the video and mark your answer. I will give the correct answer. Higher the reduction potential, stronger is the oxidizing agent. So, option B is the correct answer. So, highest reduction potential. Fluorine is the best oxidizing agent because it has highest reduction potential. Please recall the standard reaction table. Question number 12. Which of the following is not an application of electrochemical series? So please read the question. Which of the following is not an application of electrochemical series? Four options are given. Option A, to compare the relative oxidizing and reducing powers of substances. Option B, to predict the evolution of hydrogen gas on reaction of metal with acid. Option C, to predict the spontaneity of a redox reaction. Option C, to calculate the amount of metal deposited on cathode. Please pause the video, study the question again and again, and mark the correct answer. So we have to identify the which is not a part of electrochemical series. So Faraday's law is used in calculating the amount of metal deposited on the cathode. So option D is not an application of electrochemical series. Mark it. Option D. With this, we come to the end of lecture number 1 of Unit 2. Next lecture, we take up Nernst equation. Till then, goodbye.